Bismillah ar-Rahman ar-Rahim. Hello and welcome everybody. Hoping you are doing well. Inshallah, today we're going to start our tutorial regarding chapter 7, which is mainly talking about what the internal forces or loading at a specific point and the shear moment diagram. Okay, so as usual, just as a quick overview, let's say we have this beam, okay, and we have on it different types of loadings. Let's say we have a concentrated load and say for example a uniform load, okay, W and P, and say we have a fixed support, and this is a cantilever. So what's required from us is to find like a specific point. Okay, let's say here it is C, the internal loading. So we will just take a cut, okay, and take the easier part, either the right or the left side. Sometimes no need to find the reactions, such as in this case, if we take the right side, okay, so we can ignore the reactions. Now at the cut, we should adhere to the, so here is our cuts, say for example, from the right side, and here is our cut from the left side, okay? So we must adhere to the positive sign conventions of the internal loadings, which says that from the right, the shear is upwards, shear force, the normal force is going to the left, okay, and the moment is clockwise. And the for the other part, it will have same magnitude and but opposite directions. So the shear is downwards, the axial is to the right, and the moment is what, counterclockwise. Okay, so they will cancel each other. Okay, and the moment. So we can start now our first problem. Determine the internal normal force, shear force, and the moment at points C and D. So here is our point. We'll take the cuts at points C and D. And the simply supported beam. Point D is located just to the left of the 5 kilonewton force. So if we take a cut here, and if we are going to consider the right side D member DB, the force will be included, correct? Because it's just to the left of the point D is just to the left of the 5 kilonewton force. So point D is just to the left, okay, of the force. So it is included. But when we take the summation of moments about point D, we will ignore the force, but it will appear in the summation of forces in the y direction. We will see that soon. So first of all, we need here to find the reactions first. So taking the summation of moments about point A, okay, we have what? These will not be with or be included in the equation. So here we have a triangular uniform load. So the area will be half multiplied by the length, which is 3 meters, multiplied by the height, which is 3. Okay, so half multiplied by 3 multiplied by 3 is 4.5 kilonewtons. And it's acting at a distance of what? The length over 3 from this side. Okay, so 3 over 3 is, so the length is 3, and divided by 3 will give us 1 meters. So here the distance is 1 meters. Okay, and we have the concentrated force and the reaction at B. So By multiplied by the distance, which is 6, because we are taking the moment about point A, okay, and rotating counterclockwise, so positive, okay. And here, regarding the concentrated force, 5 kilonewtons multiplied by the distance, which is 3, and it is rotating clockwise, so it is negative, so minus 5 multiplied by 3. And regarding the resultant force from the triangular load, 4.5 multiplied by the distance, which is 1. Okay, here is our point A, and it's rotating what? Clockwise, so it is negative. So minus 4.5 multiplied by 1 equals to 0. So we get the reaction at B to be 3.25 kilonewtons acting upwards. Okay, now taking the summation of forces in the x direction, we'll get what? AX equals to 0, because we don't have any other components in the x direction. Now, taking the summation of forces in the y direction, we have what? We have minus 5 plus by, which is 3.25, minus 4.5 plus ay, and we will get ay to be what? 6.25 kilonewtons acting upwards. Now we are ready, after we have found the reactions, now we are ready to take the cuts at points C and D. And it's up to you whether you would like to take either the right or the left side. So here I took member BD or DB, the the, uh, the right side of point D after I had made this section or the cut. So as we have said, this 5 kilonewtons will appear with us because point D is just to the left of the 5 kilonewtons force. And we must make sure that we will put the right directions. So the shear is upwards, the axial is to the left, and the moment is clockwise, okay? Uh, so point D is located just to the left of the 5 kilonewtons force. And now we are ready to what? To write our equilibrium equations. So summation of fx will give us what? The axial nd is equal to 0 because we don't have any other horizontal components. Now, summation of forces in the y direction, we have what? We have plus 3.25 minus 5, okay, plus the shear, which is Vd, okay? So this will give us the shear at point D will be 1.75 kilonewtons acting upwards. Again, we should make sure that the directions are correct, okay, with reference to the positive sign convention. So now we have found, or still, we should find the moment at point D. So taking the summation of moments about point D, we have what here? We have minus MD because it is acting clockwise, okay? And we have also this force, 3.25 kilonewtons, acting counterclockwise, so it's positive, multiplied by the distance, which is 3. 5 kilonewtons, the force 5 kilonewtons, and the shear will not be included, okay? So the moment will be just 9.75 kilonewtons meters, and it's positive, so it's acting clockwise. Now, taking the section at point C to find the internal loadings, okay, it's up to you whether you would like to take either the left or the right section, okay? So I took actually the left part, so member AC, okay? So here I have member AC, okay, and I have this distributed load, okay? I will divide it. If you take the right side, you will just have the triangular part and the concentrated force. But in my case, I took what? Here's point C, I took the left side. So I have a triangular shape, which is this one, and the uniform distributed load, the rectangular shape, okay? So I have two parts, but I have first to find what is the value of the distributed load at point C, okay? From these two triangles, the full triangle or the complete triangle and the small triangle, okay? Let's see here, I have drawn it. Here I have the distributed load is 3 kilonewtons per meter, okay? The uniform load, 3 kilonewtons per meters. And here the total distance is what? 3 meters, okay? So it is 3 meters, and I would like to find the value of W at C, okay? Here is point C, here is point A, okay? And taking the full triangle here is point D, and here the distance is what? 1.5 meters, okay? So I will say, okay, here it is 3 kilonewtons per meters. Here I'm looking at the full triangle. Over what? Over 3 meters, the total distance, okay? Or the length of the full triangle. So over 3 equals to what? This small triangle, which is in the yellow, over omega c equals to omega c over its length, which is 1.5 meters. Okay. So we found omega c to be what? 1.5. So here the omega c is 1.5, this omega c. Okay, and here it is 3 kilonewton per meters, and here it is 1.5 meters. And here the positive sign conventions is what? The shear is downwards, the axle is to the right, and omega c is what? Acting counterclockwise. So what we have here, the left side, we have just these two distributed load, the triangle and the rectangular one, and the reaction at A, which is what? 6.25 kilonewtons. So I have 6.25 kilonewtons, and I have this triangular one, okay, which will be what? Here, the height is what? 3 will be 3.25 minus 1.5, which is 1.5, okay? So the area will be what? Half multiplied by the height, which is 3 minus 1.5, multiplied by the length, which is 1.5, will give us 1.125 kilonewtons, which is the resultant, acting at a distance from this axis or side at a distance of what? The total length, which is 1.5 over 3. Okay, so 1.5 over 3 is 0.5 meters. So here the distance is 1.5 meters. Sorry, 0.5 meters. And this distance will be what? 1.5 now minus 0.5, which is 1 meters. Okay. Also, we have the, so we are done with the triangular shape. We have the rectangular shape here. We will say the resultant will be what? 1.5 meters, which is the length, okay, multiplied by the distributed load, okay, which is 1.5. Will give us 2.25 kilonewtons acting at the middle. So here it is 0.75 and 0.75, okay? Here it's 0.75. Now we are ready to use our equations, equilibrium equations. So what? I have started with the summation of points about point C. So here it's acting counterclockwise, so positive MC. Okay, and I'm taking it at point C to get rid of the shear at C. So it's not included in our equation. Here also I have what? 6.25 kilonewtons, which is the reaction at C, at A, sorry, multiplied by the distance. Okay, and it is rotating clockwise, so it is negative. Okay, negative. Here is the distance, plus 1.125, which is the resultant of the triangular load here. Okay, from the triangular load, the distance from here is 0.5, but I need the distance till what? Point C. So it is 1.5 minus 0.5 will give us what? 1 meters. Okay. Okay, and it's acting counterclockwise, so it is positive. And regarding the final resultant, which is from the rectangular one, I have 2.25 multiplied by the distance, which is what we have said, 1.5 over 2, which is 0.75. And it's rotating counterclockwise, so this is positive, okay? So we get the moment at C to be 6.563, and since it's positive, our assumption is correct, the positive sign convention, okay? So it's acting counterclockwise. Now, taking the summation of forces in the x direction, we just have the NC. We don't have any other horizontal component. So NC will be what? 0, okay? Now, taking the summation of forces in the y direction to find the shear at C, we have plus 6.25 minus VC minus 2.25 minus 1.125 equals to 0, okay? So we get the shear to be to have a value of 2.875, and since it's positive, our assumption is correct. It is acting downwards. Okay, moving on to the next problem here. Determine the internal normal force, shear force, and moment about points E and F. So here it's our point E, and here it's F. So we have to make a cut here and here, and it's up to you whether you would like to take either the right or the left segments. But first of all, we should find the reactions. We have here a pen, so AX and AY, and here we have a tension force, which is the same as here. Okay, it's always the force or the reaction in the cable is always a tension force. So drawing the free body diagram, okay, to find the reaction, here is T, tension, and here it's also T, and we have the distributed load or uniform load, 300 newtons per meter, multiplied by the distance, which is 6, we will get 1800 newtons, okay, acting in the middle. So here it's 3 meters and here it's 3 meters. And the angle here is 45 degrees. And the reactions at now, taking the summation of forces or summation of moment about point A to find the tension force. Okay, so here it is starting with the resultant multiplied by the distance, and it is at rotating what? Clockwise, so it is negative. So minus 1800 multiplied by 3 plus T, the first tension force, okay, multiplied by the distance, which is 6, and it is rotating counterclockwise, so it is a positive. It will have a positive value. And finally, the tension force, the inclined tension force, this one. So here, the horizontal component is passing through point A, so it's neglected. It will not have any effect. And but the vertical component, which is T sine 45, will have an effect. So it's multiplied by the distance, which is 3 meters, and it is acting counterclockwise, so it is positive. Okay, so the tension force is 664.92 newtons. Now, taking the summation of forces in the x direction, we have what? Minus ax, okay, and the horizontal component. So plus t cosine 45 equals to 0, and t we have found the value, so ax will be 470.17 newtons acting to the left. Now taking the summation of forces in the y direction, we have plus ay plus t plus t sine 45 minus 1800, okay, equals to 0, and we'll get ay to be 664.91 newtons. Now we are ready to take or to make our cuts. So starting with point E, okay. So here is our cut at point E. I have put the internal loadings with reference or as the sign conventions states, okay. And the reaction, I took the left side since it will be easier, okay. Because here we have the tension force. Anyway, here the reactions at A, I have AY and AX, okay, which I have already found. And we have this distributed load, which will be 300 multiplied by this distance only. So 300 multiplied by 1.5 will give us a value of 45 newtons acting in the middle. So here the distance is 0.75 meters, okay? So taking the summation of forces in the x direction, we have plus NE minus 470.17 equals to 0. So it's obvious that the axial force at point E will have the same magnitude but opposite direction. Okay. Now taking the summation of forces in the y direction, we have minus VE, okay, minus 450 plus 664.91 equals to 0. So we will get the shear at point E to be 214.91 newtons acting downwards, since it's a positive value. Now taking the summation of moments about point E, we have what? We shall not forget this moment, okay, which is the unknown. So positive ME, because it's acting counterclockwise, these forces will not be included because they are passing through point E. We have this force, okay, which is 1664.91. multiplied by the distance, which is 1.5, and since it's acting clockwise, so it is negative. Okay, and finally, this resultant force, which is for the 450 newtons, okay, multiplied by the distance, which is 0.75, and since it's acting counterclockwise, it will be positive, okay, equals to 0, and we'll get the moment in newtons per meters, and since it's positive, our assumption regarding the direction is correct, so it's acting counterclockwise. Now we are done with the internal forces at point E. Uh, we should now move on to point F to find the internal loadings. So we will make a cut. It's obvious it will be easier to take the right side. So we have the tension force here, the resultant, okay, just the resultant and the tension force. Okay. So here is the resultant, which is the 300 newtons per meters multiplied by the distance, which is 1.5, okay, meters. And the tension force, we have already found it, the reaction parts, and we have the internal loadings. So taking the summation force in the x direction, we get the NF is equal to 0, okay, and summation force in the y direction, okay, we have what? Positive VF plus the tension force minus the resultant, okay, equals to 0. So the reaction at F will be negative 214.92 newtons. So that means our assumption regarding the positive sign convention is not correct. So it is the opposite direction. So it's acting downwards. Now taking the summation of forces in the summation of moments, sorry, about point F, okay. So the shear and the axle will not be included. We have what? Minus MF, it's rotating clockwise, positive 664 that inch force multiplied by the distance, and it's acting counterclockwise, so it's a positive, okay? And here the MF is negative because it's acting clockwise. And finally, the resultant multiplied by the distance, which is 0.75, okay? And it is what acting or rotating clockwise, so it is negative about point F equals to 0, and we will get the moment at point F in newtons per meter, okay? Now here it's a 3D problem. In the 2D problems, we have what? 3 equations, correct? Summation of forces of Fx, Fy, and the moment. 3 equations. And in these 3D equations, we have 6 equilibrium equations available. So here, determine the x, y, z components of internal loadings at a section passing through point B. So we should make a cut here, okay, or take a section. Neglect the weight of the pipe, take F1 to be this Cartesian vector notation, and F2 to be this Cartesian vector notation. Anyway, here it's preferred to use, of course, or you can use the vector analysis, but you can just put the components and use the scalar analysis, okay? Because it's a 3D problem. Anyway, here F1 is given as a Cartesian vector, but what I did is that I put, okay, we have here 200 I hat positive. So here is our x-axis, okay? So here is the component in the x direction, 200 newtons positive. Here I have the j hat component, the y component minus 100. So here is the positive y. So the 100 is in the opposite direction, the negative y axis, and have a value of 100 newtons. And finally, the z component is minus 400. So it is acting downwards. Here is it's the positive. So here it will be what? Negative 400. Now regarding force F2, I have 300 I hat. So here's the positive x-axis. So here it is 300 newtons, the x direction, and 0 of the y component. But regarding the k hat, z direction, it is minus 500. So it is acting downwards, having a value of 500 newtons. Okay. Now, after I take a cut, I will put the internal loadings, which are 6 internal loadings. the shear in the y direction, the shear in the z direction, the axial in the x axis direction, and the moments. Okay, and here are the axes. Here it is the x-axis, okay, the y-axis, and the z-axis. Okay, now we can use the scalar analysis to find these six unknowns. First of all, summation of forces in the x direction equals to 0. Okay, so I have what? Positive plus, let me erase these. So here, yes, plus an x, okay, since it's acting in the positive x direction, as our assumptions are all in the positives. See here, Vy is in the positive y-axis and Vz is in the positive z-axis. Anyway, also I have what in the x direction as the forces, axial force. I have 300 newtons, okay, plus 200 newtons. They both are acting in the positive x direction. Equals to 0, I will get nx to be minus 500 newtons. So that means the axial at point B is what acting in the opposite side, okay? Anyway, so now we are ready to take the summation of forces in the y direction. Okay, I have what? Positive Vy, okay, minus 100. That's it. I don't have any other forces in the y axis direction. Equals to 0. So Vy is equal to 100 newtons. Now, taking the summation of forces in the z direction, okay, I have what? Positive Vz minus 100. Here, the Vz, sorry, Vz minus 500 and minus 400 equals to 0, and we get the value of Vz. Now, summation of forces in the mx direction. Here we should be careful. Okay, we need just the imagination a little bit. Let's check here. The summation of forces in the mx direction. Okay, the x-axis. About the x-axis. First of all, we have positive mx. Any force that passes through the x-axis or parallel to the x-axis will not be included. Okay, so here 300 newtons, it's parallel to it or passing. Here it's passing, it will not be included. And also here the reactions will not be included. Okay, here the 100 newtons is passing through the x-axis. Also the 200 newtons is parallel to the x-axis. So we just have the 400 newtons. Okay, and applying the right hand rule, here is our distance, which is what? 1.5 meters. Okay, and here is our force. So the moment about the x-axis will be 400 multiplied by the distance, which is 1.5, and applying your right hand rule, your fingers, four fingers, like in the direction of the rotation, and you'll find the thumb is in the negative x-axis, so minus here. Okay, equals to 0, we'll get the value of the mx to be 600 newtons meters. So our assumption of the direction here is correct. Now, summation of forces and of moments about y-axis. Uh, Here is our y-axis. Okay. So again, any force that is parallel to the y-axis or passing through the y-axis will not be included. So we have here, first of all, here 300 newtons is passing through the y-axis. Okay. Here, 100 newtons is parallel to the y-axis. Here, 200 newtons is passing through the y-axis. Okay, so we just have the 400 newtons and the 500 newtons multiplied by the distance. So 500 newtons multiplied by 1 meters and 400 newtons multiplied by also 1 meters. And the direction will be what? Positive. If you like use your right hand rule, here is our distance, which is 1 meters. And the forces are rotating in the positive y-axis direction. Okay, so positive equals to 0, and we will get my to be minus 100. So my should be in the other direction that we have assumed. Finally, taking the summation of moments about mz. Okay, here is the z-axis. Here it's parallel to it. 400 is parallel to it. Okay, 300 is passing through it. Okay, so we just have what? The 100 newtons multiplied by the distance, which is 1 meters. Okay, so here is our 100 newtons. And applying your right hand rule, you will find the moment is in the z direction, negative z direction. So it's minus. Now, the 200 newtons multiplied also by the distance. So here is the extension of our force. And here's the distance till the x-axis. Okay, which is what? Which is 1.5 meters. Okay, so here is our force. And here is our distance. You will find also it is rotating in the or about the negative z-axis. Okay, so it's negative equals to 0, and we'll get the value of mz to be 400 newtons meters. Now we'll move to the shear moment diagrams. Uh, we have our equations, the derivative of the shear over dx equals to the distributed load, okay, and they assume that distributed load acting upwards, so it's positive, okay, and dm over dx equals to the shear value. So the slope of the shear equals to the value of the distributed load and for the loading, and the slope of the moment is equal to what? The shear value. This will help us to determine the directions here of the curve. I will tell you. And if we integrate, we'll get what? From the first equation, we'll get delta V, okay, or equals to the integral of the W dx, okay, which means what? The change in the shear between any 2 points, okay, is equal to the area under the distributed load curve. Okay, we will see here, I will explain. And also, integrating the second equation, we get delta M equals to integral of shear dx. So that means the change in the moment, okay, is equal to, so if we need to know the change in the moment, okay, we need to find what is equal to the area under the shear diagram between these 2 points, okay. Uh, Also, we have the method of equations, but it is not practical. So you will find like equation between any like this uniformity. So here you should find an equation here, find an equation, but it's not practical. So we are going to use these two equations or concepts. Okay. So let's start. Draw the shear moment diagram, and my advice to the students that you draw or solve as many problems as you can regarding the shear moment diagrams, because it's very important. Also in the coming courses. Now, finding the reactions. Okay, summation forms about point A. So we have what here? It is rotating clockwise. So it's negative minus 20, and here minus 8 multiplied by 3. Okay, clockwise, plus by multiplied by the distance, which is what? 5 meters. Okay, and finally this is concentrated, or the resultant is equal to 45 multiplied by the distance, which is 5 plus 1.5. So it is 6.5. Okay, since it is rotating clockwise about point A, so it is negative. Okay, and we get the value of the reaction at B, the vertical component. Now taking the summation force the y direction, we have what? We have minus AY, okay? I've assumed it to be acting downwards, minus 8, okay? Plus 67.3, which is the reaction at B, minus the resultant, which is 45, minus 45. We get AY to be 14.3 kilonewtons acting downwards since it's positive. And of course, we don't need the value of the horizontal component. So now, also my second advice is that you draw the shear moment diagrams beneath each other or under each other, under the original problem. So don't draw the shear diagram in a page and then the moment diagram in a separate page, okay? Because you will be lost. Why? Because we are going to like draw dashed lines at every either moment or concentrated load or at any reaction, okay? And of course at the start and at the end of the beam. Okay, so this is our second step after we found the reactions. Now we should note that the value of the moment will not appear in the shear diagram, just in the moment diagram. And because we are moving from left to right, so we should look at the moment from this side, from left to right side. Okay. Now let's begin with the shear diagram. We have what? First of all, we will go downward a value of 14.3. Okay, so minus 14.3. Then we don't have any change in the shear diagram, in the shear value. Okay, so we will move a constant value of minus 14.3. Then we have a concentrated force of 8 kilonewtons. So minus 14.3 minus 8 kilonewtons. Okay, so we will be at value of minus 22.3. Then we don't have any change of shear, the shear value or shear force. Then we'll move constant value, and the reaction at B is 67.3. So minus 22.3 plus 67.3, we will be at 45. And then since it's a distributed load, here it's a first degree, so we will go down a value of minus 45. Okay, we'll go down a value of minus 45 degrees, as we said. It's assumed that the W is positive upwards. Okay, here we can note that we can use this to determine the direction. Here, the value of the loading is what is constant 15 in the negative value because the positive is upwards. Okay, so the slope of the shear will be what? Will be constant and have a negative value. So if the slope, let me explain this. If the slope is positive, okay, the slope will be either the curve will be either in this way or in this way, because they are both like going up, but it's negative. It's what? Either this way or this way. Okay, but here let me first complete the moment diagram, and then I will go back here. Here the area is what? 2 multiplied by minus 14.3. Okay, so it's minus 28.6, and here it's a constant or 0 degrees, so here it will be first degree because we are integrating. Okay, so then we have what? A moment, which is from this side, it's going upwards, so we will say minus 28.6 plus 20, we will be at value of minus 8.6. Okay, then here the change in the area is what? Is 1 multiplied by minus 14.3. So we will go down minus 8.6 minus 14.3 will be at minus 22.9. Again, here the change, the area is negative. So minus 22.9 minus the area, which is 2 multiplied by minus 22.3 will be at a value of minus 67.5. Okay. And here the area is positive, and the area is what? Half multiplied by 3 multiplied by 45. We will get plus 67.5. So we will, it must close at 0. Otherwise, we have a mistake. Okay. Now, here it's a first degree. Here it will be a second degree. But how? Here we can notice that the slope is positive. Okay. The slope here is positive. Here, the value is decreasing positively, the value of the shear, okay? The value of the shear is decreasing, but in the positive, correct? So here the slope here should increase, or sorry, decrease, but positively. So the slope is positive, so it is going upwards, okay? So either this curve or this curve, but we have said it is decreasing positively. So it's decreasing. So the slope here is what? Is maximum because it's a vertical line. But here it is a horizontal line, so it is 0. Okay? So we will use this curve because it is decreasing from maximum to 0. Okay? So if we have drawn it this way, it's wrong. Why? Because here the value of the slope is 0 because it's horizontal, and here the value is maximum. Okay? So that's why we are using these two equations. Like this, the slope of the moment depends on the shear value. Okay, and the slope of the shear depends on the loading. Okay. Now let's move to the the final problem, and here we are going to have a cut here. Okay, I will tell you why, but first of all, we should find the reaction. So taking the summation of forces at the moment about point B, we have minus AY, because it's clockwise, multiplied by the distance, which is 6, okay? Also here, the resultant will be what? The area, which is half multiplied by 6 multiplied by 12, which is 36, and it will be a distance from this side of 6 over 3, okay, which is 2 meters. And here it's 6 kilonewtons. So anyway, here the resultant is the moment of the resultant will be 36 multiplied by the distance, which is 2. Okay, about point B, we are thinking the moment. And it's positive because it's counterclockwise. So plus 36 multiplied by 2. And here we have what? 6 multiplied by the distance, which is 3. But it is rotating clockwise, so it is negative. So minus 6 multiplied by 3, and the AY will be 9 kilonewtons acting upwards. Now, taking the summation of forces in the y direction, we have plus 9, okay, which is the value of the reaction at A, the y component, minus 36, it's acting downwards, plus By, which is the unknown, minus 6 equals to 0, and we will get the reaction at B. Okay, now we are ready to draw a shear moment diagram. Here, we have a triangular uniform. Okay, so the shear will be a type, the shear diagram will be a type of, the curve will be of second degree. Okay, so we know that it will take this shape. Okay, here it is increasing, the value is increasing of omega in the negative value, because we said that the positive is upwards. Okay, so the slope should what? Increase in the negative. Okay, should increase negatively. So the slope, the curve is going downwards, because here it is 0 and here it's maximum, and the slope is so it is the slope here is decreasing but negatively because it is going downwards. Anyway, so if we have drawn it this way, it's incorrect. So here it's a second degree, but how to find this the intersection location and this value? So we know here it is 9 kilonewtons. Okay, so we will take a section here and get the Vx equation and equate it to 0, and we will find the intersection or the point where the shear is 0. It will be 3 meters. And then, okay, we are going to get the moment equation and say that at x equals to 3 meters, how much is the value of moment? We will get from the equation 18. And then I can say, okay, when substituting by the moment equation of value of x6 of x equals to 6 meters, I will get the moment at distance of 6 meters, because here the equations of AB is applicable from x equals to 0 till x equals to 6 meters. So here what I did for part AB, I take a cut, okay, and x is from 0 to 6 meters. But I should find the loading at the cut in terms of x. So here the default triangle is what? 12. Here it's 12 over 6 meters. And I will say, okay, at the cut, I will say it is omega x over x. Okay. So 12 over 6 equals to omega x over x. Here it is x. So omega x will be 2x. Okay, here it is 2x. And here are our loadings. So taking the summation of force in the y direction, I have plus 9, okay, minus the resultant, which will be what? Half x, which is the length, over the height, which is 2x. So half multiplied by 2x multiplied by x will be x squared. Okay. So here it's x squared, the resultant, and minus Vx. Okay, minus Vx equals to 0. So the equation of the shear will be minus x squared plus 9. I took the shear to the other side, shear Vx. So equating it to 0, okay, so minus x squared plus 9 equals to 0, we'll get x equals to 3 meters when the shear is 0. So here x is 3 meters, okay? Now, getting the moment equation, okay, here it's mx positive because it's acting counterclockwise, okay, and I have this, it's clockwise, so minus 9 multiplied by x, okay, so minus 9 multiplied by x, and finally, the resultant, okay, which is acting here, and so it's x squared multiplied by x over 3, and it's rotating counterclockwise, so it is positive, okay, check. Here, x squared multiplied by x over 3 equals to 0. So we get the moment equation and notice here the degree. Here the shear equation is of degree of 2, and here the moment equation uh, of the third degree. So now to find the moment when x equals to 3 and when x equals to 6, just plug in or replace x by 3 and 6, and you will get 18 and minus 18. So at x equals to 3, it is 18, and at x equals to 6, it is minus 18. Okay, and the curve will be what? Of the third degree. Okay, now here you can note that here the values are what? Are decreasing negatively. Okay, so here the slope should be what? Or sorry, here the first part, the values are positive. Okay, so the values are what? Decreasing, like here it is 9, then here it is 7, let's say here it is 6, so they are decreasing positively. So the slope should be positive first of all, so it is going up either this way or this way, but it is decreasing. So here the slope was maximum, and here it is 0, so we'll choose this one. Here it was 0, then maximum, here it is increasing, but in our case it's decreasing. Similarly here, the values are what? Increasing. Here it's minus 25, let's say. So they are increasing, okay, negatively, okay? So the slope should be negative, so it is going downwards either this way or this way. But it is increasing. So we'll choose what? Increasing, here it is 0, then here it's maximum. So we'll choose this one. Here it is maximum, then it is 0, here it is decreasing, okay? So, and finally, here the area is what? Will be 3 multiplied by 6, which is plus 18. So it will close at 0. Here it's a constant. Okay, so here it will be first degree. Okay, it's going up because it's increasing. Okay, so the values here are constant but positive. So the slope here will be constant. It will not be changing, but positive. So it's going up. Okay, by this we conclude our tutorial. Hoping that was clear, and thank you for your time. Good luck.